This is Form A from the warm-up quiz from last week. I'm going to work through all of the different forms, A, B, C, and D, along with the makeup version. Each of them has a different question that's covering something slightly different, so it would help you to review all of them, but obviously if you want to just look at the one that you took, you're welcome to do that in order to figure out what portions of you got right and what portions of you got wrong. So this is Form A. Form A says, Charles uses positive 25 newtons of force to push a 12 kilogram block for 2 meters from rest across a frictionless platform. It then slides until it collides with a 6 kilogram ball initially at rest. Calculate the work done on Charles when he pushes the block from rest. That's part A. Obviously, we have other questions about the same scenario. The scenario has two different parts. It has a section of motion where Charles is using a force to move a block. So Charles is doing work, which is what we're going to be analyzing in part A. And then after he does work, then it's moving because he pushed it. And so once it's moving, there's going to be a collision. So again, there are two different parts of this to analyze, starting with the work done. If you want to calculate work, you can do so in one of two ways, depending on what information you have. You can solve for work by looking at the change in kinetic energy. If you happen to have that information, you could take a look at what the change in energy is of the block. However, I don't know how fast it's moving after he pushes it, so I actually am not able to use that particular method. The other way we can solve for work is simply using the work equation. Force times displacement, and I do have both pieces of information to do that. So that's what we're going to do, is work equals force. In this case, the force is 25 newtons, and the displacement is 2 meters because that's how far he pushes it with that amount of force, giving us a work of positive 50. And the unit here is joules or Newton meters. Since this is newtons and this is meters, that is a joule. So this is the answer to part A of number 1. Part B, what is the velocity of the block after he does work on it, but before the collision? So after he pushes it and he does 50 joules of work on it, it's going to be moving. And that's where we use this equation. We couldn't use it in part A because we didn't know how fast it was moving, but now that we know how much work is being done, we can use the work to figure out how fast it's moving because it was initially at rest. And so the initial amount of kinetic energy will be 0, meaning that the work done will be equal to the final kinetic energy that it has. And so that's what we're going to do, is that the work is equal to the change in kinetic energy, but because the initial was 0, again, change is final minus initial, this one's going to go away. And so it's just work equals final kinetic energy. The work, of course, was 50 joules, and the kinetic energy equation is 1/2 mv squared. The mass of the block is 12 kilograms. And we can then solve for the velocity after it gets pushed. Okay, so this is going to end up being divide both sides by half of 12, which is 6. Okay, so 50 divided by 6, let's go ahead and put that in the calculator. It is giving me fractions. All right, by the way, if you don't know how to fix the Inspire when it gives you fractions, you're going to use the dock button right here, and then option 7, settings and status, option 2, document settings, and then the issue you're having is down here where it says calculation mode. You have to change it from auto to approximate. So if it's doing that to you, that is how you go about fixing it. And then there's my mouse. Come on. All right, try that again. There we go. Okay. There we go. 8.333, repeating. So v squared equals 8.333333. And again, that's v squared. So your next step is to take the square root of that value. On the Inspire, the square root button is right here above the squared button, so you have to use the control button to get to that. And then fill that in, and there is your velocity. So the velocity after the work is done is 2.89, if I round it, meters per second. And it's positive because he was pushing it in the positive direction. Okay, so that's part B. Part C. After colliding with the block continues to move forward with a velocity of positive 1 meters per second. What is the final velocity of the ball after the collision? Again, when we're analyzing collisions, it's always helpful to look at a picture so that we can kind of visualize everything that's going on. So I know that this block is now moving, and I know how fast it's moving. Again, that was the whole purpose of the previous part, 2.89 meters per second. And it's going to collide with this ball that is initially at rest. It says it up here, initially at rest. So the velocity of this is 0. And then after the collision, it tells us that the block continues to move forward. So there's my before collision picture, and then afterward it's still going this way. It's just slower. Now it's only moving 1 meter per second, and that means that it's going to have transferred some of its momentum to the ball. So the ball is now going to be moving this way. I just don't know how fast. And so that's what we're trying to figure out, is how fast this ball is moving after the collision. So again, what I would recommend that you do is, and I might need that information actually, is label everything that we know. So I'm going to call this object 1 and this object 2, and so M1 is going to be the mass of the block, which it says up here is 12 kilograms. V1 initial is the 2.89 that we found in part B, and again you can put your units on here, kilograms and meters per second if you want. I just don't have a ton of room. Mass of object 2 is going to be the mass of the ball, which it says is 6 kilograms, and its initial velocity is 0. And then after the collision, the masses aren't going to change, so M1 and M2 are still going to be 12 and 6. But we do have different final velocities. V1 final is only 1 meter per second, and we're looking for V2 final. And so that's your setup. Okay, so from here you plug it into the conservation of momentum equation. That is this equation right here, M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So that is the equation we're substituting into. Our mass, M1 is 12. This is going to be 2.89 plus M2 is 6 times 0 equals, this is going to be 12 times 1 plus 6 times V2F. So that's your substitution step. So now we're going to go to the calculator. This is obviously going to be 0, so I'm not going to worry about that. And we need to multiply this velocity, 2.89 times 12. That gives us 34.641 for this side. And then this is going to be 12. 12 times 1 is 12. So I need to subtract that 12 over here. Again, do not add these. These are not like terms. This one has a V2F attached. This one does not. Okay, so you're going to subtract the 12 instead. Some of you are still making algebra errors. Minus 12. Okay, and so that leaves you with this 22.64 equals 6 times V2F. Okay, we're not done yet, obviously. Okay, but that's what you get whenever you solve this side and then subtract 12. And then from here, all you have to do is divide by 6. So divide our answer by 6. And that gives us our velocity. V2F will be equal to 3.77 meters per second. All right, let's look at the last question for part A. which looks like this. It says the block and ball are represented by the box and circle in the diagram below. The diagram shows velocity vectors for the block and ball both before and after the collision. Points R, S, and T label various positions of the objects. Velocity vectors are not drawn to scale. So this is what we just saw. We had in our picture the block moving and then the ball at rest. They collide, and this is what we had afterward. They're both going that way. We just found out how fast. The question, though, says a student sketched the following free body diagram for the ball at position T. Do you agree with this student's free body diagram? If yes, explain why it is correct. If not, explain problems with the diagram and refer to specific physics principles. So we're looking at what a free body diagram would look like at this position. And when I look at this, I should always expect to see this, so that looks good. And a normal force, because we're still on the surface here. Okay, and so it doesn't say that we've left the surface, and these should be equal and opposite to each other, which they are. You can count the boxes to see that these are the same length, but you're looking for that as well. The issue is this one right here. There is a force from the block. However, that force happens right here during the collision. This is after the collision has occurred, and at this point in time, there is no longer a force from the block being applied. That force from the block only gets applied during the collision itself when they're in contact. Yes, it's moving to the right, but that doesn't mean there's a force to the right. If there were, it would be accelerating. It's not. Okay, we figured out how fast it was going back here in part C on the other side of the page. It's not speeding up, it's going at that speed due to this. The acceleration happened here when it went from being at rest to moving. So this force should not be drawn. So you need to say, do you agree with it? No. Okay, there should be no force. No force from the block after the collision. Okay, so you can say F block only occurs during the collision, something like that. But that is your answer to part D. You should disagree with it, and that force should only be applied during the collision. By the way, the force that the block applies to the ball and the force that the ball applies to the block should be equal and opposite to each other. You could mention that too. That's Newton's third law. All right, so that was part A, or rather Form A. This is Form B. It is a similar problem, but it does have different questions, and we're going to be kind of solving things in a little bit of a different order because of that. This one says, in a lab experiment, Charles observes a 12 kilogram block moving at 3 meters per second before colliding with a 6 kilogram ball initially at rest. After the collision, the two objects stick together and continue moving forward. So this is a different scenario. There's no work on this one. Instead, we have just this object that's already moving, and it's a different type of collision. The last one was a bounce apart. This one is a stick together. So again, the first thing we're analyzing here is the collision itself. We're not worried about this continue moving forward yet. We'll figure that out in a minute. But actually, the velocity we get here will be the velocity with which they continue moving forward. And we'll use that in the next part. So again, if you have a collision, it's always a good idea to draw a picture. I'm going to draw it up here at the top. I have my block. That way I have more room to work down here. My block is initially moving at 3 meters per second, and it's going to collide with the ball, which is initially at rest. And then after the collision, and my pen is running out of ink apparently, so let me get something else to write with. After the collision, now we have the two objects just kind of stuck to each other, and they're moving together as one unit. And the question is, how fast is that? Okay, so that is our setup for this problem. So if we want to calculate the velocity, again, we're going to treat this as conservation of momentum. We need to label all of our givens. M1, I'm going to call my block 1 and my ball 2. M1 will be the mass of my block, which it says is 12 kilograms. V1 initial will be the 3 meters per second that it's initially traveling at. M2 is going to be the ball. Its mass is 6 kilograms, and its initial velocity is 0 because it says it's initially at rest. After the collision, again, my masses don't change, so what we're going to be looking at afterward, I'll do this, is just the velocities, so V1F and V2F. Now the thing about this particular problem is that because these things stick together, these two things are the same. So rather than having V1F and V2F, which would imply that we have two different velocities, we can instead just call it VF, because if you have a stick together collision, they're going to have a shared velocity at the end. And that's what we're looking for, is what that shared final velocity is. Now, because they're stuck together, when they're moving at the end, the mass will be the total of the two. It'll be M1 plus M2. Your total mass there is going to be 18, which we'll see in a minute when we do the math. So again, we're going to go back to the equation. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. That's the full equation. If you want to use the shortcut for stick together, you can, which I'll be doing in just a second. I'm writing out the whole equation first. When I substitute in, this is going to be 12 times 3 plus, I'm not going to write out 6 times 0, I'm just going to write 0, equals, and here's where you have kind of a shortcut because we don't have V1F and V2F. It's just VF. And so because of that, whenever you plug in, you're going to have your 12 VF plus your 6 VF. These are now like terms. Or if you want, you can say, okay, let me factor out the VF, okay, which still results in you adding these together to get 18 times VF. Okay, and so again, that's the mass I said we were going to end up with for the total. And that's exactly what we get. So this is 18 VF over here. On the other side, 12 times 3 is 36. And then to find our final velocity of the two objects together, we just have to divide both sides by 18. You should be able to do that one in your head. Okay, but if you don't know off the top of your head what 36 divided by 18 is, you can type it in the calculator. It's going to give you 2. So VF is 2 meters per second. All right, part B. Part B says, after colliding, the two objects slide over a 4.5 meter rough surface while friction applies a -2 Newton force. What is the work done by friction as they slide on the rough surface? So the last one, the work was at the beginning to get the thing moving. In this case, the work's after the collision, and it's negative work this time instead of positive. Again, you can find work if you know what your change in kinetic energy is. If you know your velocity when it starts to slide, which happens to be the velocity we found here at the end of the collision, 2, and you knew the velocity after it goes 4.5 meters, which we don't know, but if we did, we could use this. We don't have that, so instead, we're going to use the work equation, force times displacement. The work will be equal to the force, which is -2, times the displacement, which is 4.5, and both of those numbers are in the question. That gives us a work of -9 joules. Part C, after sliding across this rough surface, what is the final velocity of the ball block system? Again, I wasn't able to use this equation here, but I can use it to find this. Now that we know what the work is, we can set the work equal to delta KE. The work is -9. And so we can say -9 joules for my work equals, and then change in kinetic energy will be the final kinetic energy minus the initial kinetic energy. That's your equation for change in anything, is final minus initial. We know what the initial velocity is. Now I know up here I labeled this as VF, but there are two parts to this question. There's a collision, and then after that collision, this thing is moving, and then when it moves, it encounters some frictional surface over here. So the velocity that we got here becomes the initial velocity when it starts to go over this frictional surface. So even though it says VF here, it's actually the initial velocity when it encounters the friction. So if we're trying to figure out what the final velocity is, that means how fast is it going after this work is done. And so we have our -9 equals 1/2. Now the mass we're going to use here for the KE equation, 1/2 mv squared, is going to be the total mass because it's both objects stuck together going over it. And that total mass was 18 kilograms. So we're going to say 18 times VF squared, again that's what we're looking for, minus 1/2 18 times VI squared, which was that 2 meters per second. Okay, so that is your substitution step. From here, you have half of 18, which is 9 times 2 squared. 9 times 4 is 36. This one becomes 9 times VF squared, and this, of course, is -9. Again, these are not like terms. Do not subtract them. Instead, you need to move this over here. Because it is being subtracted, you move it by addition. Add 36 to both sides. That becomes 36 minus 9. Okay? And so, if you don't know what 36 minus 9 is, you can put it into the calculator and type it in, but it should be one that you can do in your head. That gives us 27. That's 36 minus 9 equals 9 VF squared. Again, from here, we're going to divide both sides by 9. 27, again, divided by 9, probably not something you need a calculator for, but this last part is 3 equals VF squared. Again, I want VF, not VF squared, so take the square root of 3, and you're going to get a final velocity of 1.732 meters per second. All right, again, there is a back, so let's flip it over and see what it says. Part D says the block and ball are represented by the box and circle in the diagram below. The force from the collision experienced by the 12-kilogram block is represented by the arrow in the diagram. Sketch a force vector for the force acting on the 6-kilogram ball in the diagram above. Be sure to accurately represent the magnitude and direction of this force, and then explain your reasoning. So yeah, after they collide, they do end up going this way. Okay, that's what the question said. And that's what we calculated earlier. They end up going that way. However, during the collision itself, there is a force applied to each of them before they stick together, or really that causes them to stick together. And again, this is going to represent a force pair. So you're going to draw a vector going this way that it's the same length, 1, 2, 3, 4, 1, 2, 3, 4, equal and opposite. Okay, and so that's what you're going to tell me down here when you explain it, is that this is Newton's third law. For every action, there is an equal and opposite reaction. This constitutes a force pair. You need to write something about that here. All right, so those are parts A and B, or rather forms A and B, which were the ones that the morning classes had. Now we're going to take a look at parts, or rather forms C and D, which are the ones that the classes in the afternoon had. Again, depending on what time you came to class, you have a different form here. So again, all of these are going to be valid, but you can look at yours specifically if you want to focus on that. All right, this is form C. It says a 2-kilogram ball is released atop of a 3-meter high ramp. A 6-kilogram block rests on a level surface at the end of the ramp. The ball rolls down the ramp and along the level surface before hitting the block. Neglect friction. So we know that this ball is at the top of this ramp and that the block is down here somewhere. Okay, and that this ball is going to be released from rest. So it's going to start to travel downhill. And it's going to convert the energy that it has. Oops. And let's put the height here. It is 3 meters. But it's going to convert the energy from gravitational potential energy to kinetic. Okay, so the first part of this particular problem starts with energy being converted from one form to the other. And we're going to actually start by calculating what the initial gravitational potential energy of the ball is before it's released. So just up here, the GPE equation's pretty straightforward. mgh, that's it. And so we're going to take the mass of the ball, because that's what it asks for, which is 2, gravity, which is 9.8, and the height, which it says is 3. And you're going to multiply those together. All right, so that ends up being 6 times 9.8, which is 58.8. The next one says, how fast is the ball moving at the bottom of the ramp before colliding with the block? Again, to answer this, we need to think about this in terms of energy transfer. We're going to be converting energy from GPE at the top of the ramp. That ball has gravitational potential energy. It's released. It's from rest, and so it only has GPE up there. And the amount of kinetic energy it has at the bottom once it gets down here will be due to the gravitational potential energy it had up there. And so if we want to figure out how fast it's moving before it collides, it's just energy transfer. It goes from GPE to KE. Again, we want this, we already have the GPE as 58.8. We could put MGH, but we already did that. So let's go ahead and just take the 58.8 and set it equal to our KE. Again, we don't want energy though, we want how fast, so we're looking for the velocity. So again, let's plug in our equation for KE, which is 1/2 mv squared. The mass of the ball is 2, and so 1/2 mass times v squared looks like that. Half of 2 is 1. I'm not going to worry about 1 times v squared. Okay, and so v squared is 58.8, which makes v the square root of 58.8. So we're going to do that in the calculator. And when we take the square root of 58.8, we get this value right here, 7.67. All right, so that is how fast it's moving right here. Okay, 7.67 meters per second. All right, and then it's going to collide. Okay, so now we're dealing with the collision. We have this ball moving at 7.67 meters per second. It's going to hit this block that is initially at rest. That's what it says. The block rests, so that's 0. They're going to collide, and then the ball's going to bounce backwards. So again, if you wanted to draw in a picture of what's going on, there's my before collision, and then afterward my ball's going this way at 1 meter per second, and the question is, what is this block doing? What's its velocity and what's it doing? All right, so let's go ahead and label all of our givens. Actually, I need the information from that, don't I? All right, so I'm going to call the ball 1 and the block 2. So M1 is going to be the mass of the ball, which is 2 kilograms. V1 initial is going to be the velocity of the ball initially, which is what we found up here. It's how fast it was going at the end of the ramp, and that is 7.67 meters per second. M2 will be the mass of the block that gets hit, which is 6 kilograms, and V2 initial will be its initial velocity, which is 0. And then afterward, their masses aren't going to change, but their velocities will. So V1F is -1. Again, it's going this way. It says it even has a negative sign right there. And the question is, what is V2F? We're going to go back to conservation of momentum. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And when we substitute in, it looks like this. 2 times 7.67 plus 0 equals 2 times -1 plus 6 times V2F. So that is your substitution step. I'm going to use the whole value from my calculator. So I'm just going to take my answer and multiply it by 2. And that gives me this, 15.336 equals, this is going to be -2 plus 6 times V2F. Again, please don't add those. These are not like terms. Instead, you need to move this over here because it's a negative value, which means you're really subtracting 6V2F minus 2. We're going to add 2 to both sides. That will cancel this. So we're going to add 2 to this as well, giving us 17.336 equals 6 times V2F. Again, to solve for that velocity, we're going to divide both sides by 6. And then we'll get V2F equals this, 2.89 meters per second. And it's going to be a positive number. Again, I don't have a negative sign in front of it, so it's a positive value, which makes sense. It does need to go this way in order for momentum to be conserved. All right, there is a question on the back, so let's turn it over. It says, the ball and block are represented by the circle and box in the diagram below. The diagram shows velocity vectors for the ball and block both before and after the collision. Points R, S, and T label various positions of the object. Velocity vectors are not drawn to scale. So this kind of matches the picture I had on the front. It starts from rest, it goes down the ramp, now it's moving before it hits this block, and then after the collision, which happens right here, the ball's going one way, the block's going the other. And we just found the numbers that go along with those vectors. The question, though, says a student sketched the following free body diagram for the block at position T. So it's talking about this position right here. Do you agree with the student's free body diagram? If yes, explain why it's correct. If not, explain problems and refer to specific physics principles. So again, free body diagram for this block absolutely should have gravity. It does. It should also have normal force, and that normal force should be equal and opposite to gravity. It is. Again, because it's on a surface, it needs to have that as well. The question then becomes, what about this one? There is a force from the ball on the block, but it happens right here during the collision. As soon as they're not touching each other anymore, which it's not once it gets to point T, once there's no longer contact, there is also no longer a force here. Okay, and so do you agree? No. There should be no force from the ball. That only happens during contact or something like that. You're only going to get that force when the ball is in contact with it during the collision itself. Add something like that to your explanation, and if you want, you could even say that the force that the ball applies to the block equals the force that the block applies to the ball during the collision, but not afterward. All right, that was Form C. Let's take a look at the last one, which is Form D, and then I do have a makeup version as well that we can look at. Form D says, a 2-kilogram ball moves at 12 meters per second across a horizontal surface. When it collides with a 6-kilogram block at rest on a level surface sitting in front of a ramp. After the collision, the ball sticks to the block and the two objects move up the ramp together, neglect friction. So instead of it starting at the top of a ramp and rolling down, in this particular problem, the collision sends them uphill instead. So we're still going to be dealing with a similar type of problem, but it's kind of going the opposite direction. In this one, we actually have to start with the collision because the collision happens first. This one tells us that we have a ball that is moving 12 meters per second, and then it collides with this block that's at rest. And then after the collision, it says that they stick together. So this is a stick together example, and that ball and block are going to move as one unit afterward, and they'll be stuck together. And so our task now is to figure out how fast they're moving, and we have to use conservation of momentum to do it. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. That is your equation. Our masses for object, I'll call the ball 1 and the block 2. For the ball is 2, its initial velocity is 12. This one has an initial velocity of 0. If you want, you can write 6 times 0, but 6 times 0 will be 0, so I'm just going to go straight to 0. And then over here I have my mass of my ball is 2, and we don't know how fast it's moving. That's the question. However, I do know that V1F and V2F are the same because they're stuck together. However fast one is moving, they're both moving in a stick together. That's kind of the shortcut for this. So instead of calling it V1F and V2F, I'm just going to call this VF because it is a shared final velocity. There's not a 1 and a 2 anymore. They're stuck together. Plus, my second object's mass was 6, and it also is moving at VF, which makes these like terms, which means you can add them. 2VF plus 6VF, I can add that. That's 8VF equals 2 times 12 is 24, plus 0 is still 24. To find VF, divide both sides by 8. 24 divided by 8 is 3, so VF is 3 meters per second. Okay, specifically positive 3, since it's moving in the same direction that it started. All right, so that's how you do part A. Let's go ahead and take a look at part B, which says, what is the kinetic energy of the ball block system immediately following the collision? So this is immediately following the collision. That's how fast it's going. If I want to find the kinetic energy there, I just use the kinetic energy equation. However, when I do it, I need to make sure that my mass is the combined mass of both of them because they're stuck together. So it's this 2 plus 6, it's this 8. That's going to be my mass that I use. 1/2 8 times 3 squared. Okay, half of 8 is 4, and that's going to be 4 times 3 squared, 4 times 9. 9 times 4 is 36. So the kinetic energy will be 36 joules. Part C. After colliding, the two objects slide up a frictionless ramp. If they slide until they come to rest, what height do they reach on the ramp? So now we're dealing with the scenario where we have these two things that are stuck together. They're moving at 3 meters per second on this surface, and then they're going to go up a hill. And the question is, how high do they go? Okay, and so here, in order for us to figure this out, this is a situation where we're looking at how the energy that's involved and how high we can get is going to be determined by how fast we're going. The kinetic energy that we have at the bottom initially will be equal to the gravitational potential energy that we reach at the top, or wherever it is that it comes to rest. It's telling us when it says this that there's no KE. The KE will be 0, which means we're looking for the point at which this completely converts into this. And so that's what my energy transfer equation is going to look like. Again, I don't want things in terms of energy. I want 1/2 mv squared equals mgh. When you look at this, you'll notice those masses are on both sides. You can cancel them out if you want, or you can plug them in. It doesn't matter. It'll get you the same answer at the end because they're going to end up canceling each other out anyway when you do the math. But it does make the math a little bit faster if you cancel them. You can only cancel them if they're in every single term, which they are. There's only 2 terms here. But if you had like work or something over here, force times distance, you can't cancel mass. There's not mass in that. So again, be careful when you're doing that, or just plug in the number. But this is going to be 1/2, and the velocity it starts with is 3. I know it says final here because that is the final after the collision, but after the collision happens, it's now moving this fast when it gets to this. So this becomes the initial kinetic energy that it has when it starts to climb the hill. So my initial velocity at the bottom of the hill will be my 3 squared. Okay, and then 9.8 times h, and we're solving for h. So half of 9, because 3 squared is 9, half of 9 is 4.5 equals 9.8 h, and then we're just going to divide both sides by 9.8, so 4.5 divided by 9.8. And that gives us this, 0.46, if we round it, meters. All right, again, there is a back. Let's go ahead and take a look at part D. Part D says, when the two objects collide, they move forward together. The force experienced by the 6 kilogram block during the collision is represented by the force vector pictured in the diagram below. How does the force experienced by the 2 kilogram ball compare to the force pictured for the 6 kilogram block during the collision? Sketch the force vector acting on the ball, represent its magnitude and direction. So when they collide, and it doesn't matter if they stick together, bounce apart, whatever, it doesn't matter. Okay, when you have a collision, the forces will be equal and opposite. This is Newton's third law. This is a force pair. So we want it to be equal in length. 1, 2, 3, 4. 1, 2, 3, 4. Make sure you draw it so it's equal in length. And then you can say something about Newton's third law. For every action, there's an equal and opposite reaction. This needs to be equal to this, okay, because of Newton's third law. So when you sketch it, draw it equal in length and then explain why. And you should probably put more than this, but you should say that you drew it the same length because of Newton's third law, stating that for every action there's an equal and opposite reaction. These constitute a force pair, something like that. All right, so again, that is the last form that was done in class. The only thing left is the makeup version for people who were absent, which looks like this. This one says, may as well work it out, give you another example to look at. This one says a 2 kilogram ball travels at 4 meters per second when it collides with a 6 kilogram block that rests on the edge of a 1.4 meter high lab table. The collision causes the block to be launched horizontally, neglect friction and air resistance. If the 2 kilogram ball bounces backward with a speed of 2 meters per second, how fast does the 6 kilogram block move following the collision? So we're dealing with a collision here. So when we have a collision, we're going to analyze it in terms of momentum. A picture would also be helpful. So before the collision, we have this ball moving at 4 meters per second when it collides with the block at rest. And then after the collision, the ball bounces backwards. So the ball is now going this way at 2 meters per second. And the question is, what is this doing? Okay, I know it gets launched off the edge, so I do know it goes that way. So anyway, let's go ahead and take a look at how we solve this. We're going to want to label everything. So we're going to call the ball 1 and the block 2. M1 is going to be the mass of the ball, which it says is 2 kilograms. V1 initial is 4. M2 is the block. It has a mass of 6. V2 initial is 0. It's initially at rest. Okay, and then after the collision happens, the ball V1 final, again V1 initial, V1 final, sorry about that, is -2, and we're looking for V2 final. All right, that's a 1. All right. So again, we're going to go to conservation of momentum. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. M1 is 2. Initially, it's moving at 4 meters per second. M2 is initially not moving, so when I multiply by 0, that will be 0. The masses don't change, so it's still 2 here, but now it's moving backwards. Don't forget that negative sign. Plus M2 is 6 times V2F. So that's your setup. This is 8 equals, this is -4 plus 6 V2F. Again, don't add those. They are not like terms. Instead, you're going to move that 4 over here by adding. That's going to make this 12 equals 6 V2F. And if you have 12 equals 6 V2F, divide by 6, V2F is 2. All right, second part B. Is kinetic energy conserved in this collision? Show your work. So if there is conservation, that means you have the same amount before and after. Obviously, beforehand, there's only kinetic energy in the ball, but afterward, they both have kinetic energy. So I need to figure out what they both are at the end, but start at the initial amount with just the ball. So the initial kinetic energy is 1/2 the ball's mass, which is 2, times the ball's velocity, 4 squared. So the initial amount, half of 2, of course, is 1. So 1 times 16. That's your initial amount. The final amount, again, you have 2 objects here, so we need to do them both. We didn't do this one because it's not moving. But my final kinetic energy will be 1/2 times my ball's mass times its velocity, which is -2 squared. Again, when it's squared, that negative sign is going to go away. Plus 1/2 times my other object, my block, which has a mass of 6, and its velocity is also 2, but it's +2, 2 squared. Half of 2 is 1, so -2 squared is 4, plus half of 6 is 3, times 2 squared is 4, 3 times 4 is 12, and guess what? 4 plus 12 is also 16 joules. So is it conserved? Yes. You have the same amount before and afterward. And again, you only get conservation in a bounce apart collision, and not in all of them, only sometimes. All right, part C. After the collision, the block is launched from the table. How far away does it land? You're finding range. So again, after the collision, we do know how fast the block is moving. We found it up here. So I know that it has this horizontal launch, and so this velocity becomes my horizontal velocity. And again, horizontal velocities don't change because horizontal acceleration is 0. So I can fill it in like that. I also know that it's a horizontal launch. It says it up here, it's a table. So I know that the initial vertical velocity will be 0. In a horizontal launch, that's always true. And vertical acceleration will be due to gravity, -9.8 meters per second squared, and the displacement vertically will be the height of the table. It's going to fall 1.4 meters, so -1.4. You're going to solve for the time using the vertical data, and once you get that, then you can find range. So this one is going to take a couple steps. So your first step is finding that. We're going to use this equation, delta x equals VIT plus 1/2 AT squared, using only vertical data. That's going to be -1.4 equals, VI is going to be 0, so that term's going to go away, 1/2 times -9.8 times t squared. This is going to be -4.9 t squared equals -1.4. Divide both sides by -4.9. The negatives are going to cancel. So 1.4 divided by 4.9, and then take the square root of that. Let's see. All right, square root of that. Okay, sorry, calculator's being weird. All right, so my time is 0.5345. And now we're going to use that time to figure out our range, because it's the same time over here. Range horizontally is velocity times time. So we're going to take the time we just found and multiply it by 2 because that was our horizontal velocity. And we get our range of 1.07 meters. And that's your answer. All right, again, there is a back. Flip it over. It says, a student sketched the following free body diagram for the block after it has left the tabletop but before it lands on the ground below, so it's in mid-flight. Do you agree with the student's free body diagram? If yes, explain why it's correct. If not, explain problems with it. So again, we're dealing now with a block that has left a table as a projectile. And at some point, like right here, what does the free body diagram look like at that point? That's what we're looking at. And at that point, there's no normal force. We're not on a surface. There's also no force from the ball. That force only happens during the collision. So the free body diagram should only have the force of gravity because that's the only force acting on an object in free fall. So you should say something about that in your explanation.
Brazil, if you're in the building, please come to the front office.